Hi, welcome to office hours. How's the focus? How's the focus? Can you hear me?
It's good.
Hi, Divine. I just got your email and I asked which one you wanted to join.
Yes, I'm gonna respond to the
Okay,
email.
that sounds good. Hey, Kristen.
Hello, how are you?
Well, how are you?
I'm good.
Good. What can I help you with?
I just really wanted to go over just basically the beginning of the course, just to refresh my memory on some of the things from early on.
All right. So what in particular would you like to talk about?
Um, I had some troubles on some of the quizzes with subsets and elements. So I want to refine that.
Limits, elements.
Yeah, elements and subsets.
Okay. So let's review our definitions. Okay.
Okay.
That's section 1.2. All right. So our first definition is uh, uh, given a set, call it A, the elements of A are the objects that constitute the set's contents. All right. So our notation for element of would be something like X is an element of A. Okay.
Sorry, Miss Good, before you continue, I'm about to leave the meeting to go to the hospital right now. I will join once I get there.
All right. See you when you get back or when you can rejoin.
Thank you.
X is an element of A. And then if something is not in A, like Y is not an element of A, we would write it like this. Y is not an element of A. Okay, so shall we look at an example?
Yes.
So let's say A is listed like this. X in Z such that 1 is less than or equal to X is less than or equal to 5. Okay, so let's write A using what we call set roster notation, where we can just see the elements listed next to each other. Um, see the elements listed there with commas between the elements. So that's set roster notation. All right. So if we were going to do that, we would write A equals, okay, can you tell me what would be in set A?
Um, 1, 2, 3, 4, and 5.
Good.
Excuse
Yep, it's going around. And then we can write some true statements involving the element of, or not an element of. Okay, so let's do that. Can you give me a statement that we could write that would be true that uses the element of symbol for this set A?
Say it one more time.
Can you give me a true statement involving the symbol, the element of symbol, uh, true about this set A?
Um, would it be one is an element of set A?
Mm-hmm. What else would be true?
Um, two as well. Two is an element of set A.
You're exactly right. You see how that goes?
Yeah.
And then maybe the last one we might write would be 5 is an element of A, right? Now we can write some true statements involving not an element of. Can you think of something that's not an element of A?
Uh, six.
What?
Six. Like the number six.
Yeah, 6 is not an element of A. 0 is not an element of A, for example. All right. Does that help?
Yes.
That's our element of. All right, let's look at the definition of subset of. That involves two sets. Given sets A and B, we say A is a subset of B, and it's denoted by A with this soft less than or equal to symbol for subset of. If every element in set A is also an element in set B. Okay, so our notation, looks like this. A is a subset of B, or A is not a subset of B. Okay, all right, so we'll look at an example. If we use the same A that we used before, and maybe we can let B be the set of X in Z such that zero is less than or equal to X is less than or equal to, say, 6, right? Then
Mm-hmm.
is a subset of B? Well, it might
Would
help
be
if we, yeah, what are the elements in B?
elements would be 0, 1, 2, 3, 4, 5, 6.
Good. So is A subset of B?
Yes, because it has this elements 1, 2, 3, 4, and 5 in it.
Exactly.
Okay.
All right. Is B a subset of A?
No, because of 0 and
Mm-hmm.
6.
Right. 0 is an element of B, but 0 is not an element of A, for example. Or you could use 6 to show that B is not a subset of A. Do you agree? All right. Now there are just a couple of facts that we need to understand about sets and subsets. Just some facts that we could just list. So facts about any set A. First of all, let's recall the empty set. The empty set has no elements. Okay. This is the set having no elements at all. And we have a couple of different ways that we can denote that. We can just use curly brackets with nothing in them at all, or we can use the very round circle with a slash through it. Either one of those represents the empty set, okay? And some facts about any set A is that A is always a subset of itself. Does that make sense?
Wait, A is always a subset of self because it always has the same elements.
Exactly. And the empty set is always a subset of A, and these are true for any set A. And the reason the empty set is a subset of A is because there's no elements to check. The empty set has no element X. So this in particular, fact 2, holds because the conditional statement, if X is an element of the empty set, then X is an element of A, which is actually the definition of the empty set being a subset of A, right? Because it's a subset if every element in the empty set is an element in A. But there is no element of the empty set, right? So this if then has a false hypothesis because there is no element in the empty set. And that means the statement is true by false hypothesis. And that's why we say the empty set is a subset of every set A. Does that make sense?
Yeah.
Yeah, it's in the definition of subset is technically an if-then definition.
Okay.
So, if we go up here, we can just say this A is a subset of B means if X is an element of A, then X is an element of B. That statement is true. That's what it means to say that A is a subset of B. It means that if X is an element of A, like for every element that's in set A, then that element has to be in B. Well, this if-then statement is true when we're looking to see if X is an element of the empty set, then X is an element of A, because X is an element of the empty set is true by false hypothesis. So we have a quiz, and you had homework about element of an empty set, and we had class notes about those concepts. Did you have any? And there were also WebAssign. Oh yeah, and there's the definition of a proper subset. A is a proper subset of B if two things happen. A is actually a subset of B, and B has at least one element that is not in A. In other words, B is not a subset of A. So A is a proper subset of B if A is a subset of B, but B is not a subset of A. And we can go back to our example 2, where A was a set of elements that the integers 1, 2, 3, 4, 5, and B was a set of integers 1, 2, 3, 4, 5, 6. Okay. Is A a proper subset of B? Well, let's just check. Is it a subset of B?
Yeah.
And is it true that B is not a subset of A?
Yes.
Right. A is a subset of B, checks out, right? But B is not a subset of A because, well, you already said it, because 0 is an element of B and 0 is not an element of A. But you could also say, hey, 6 is an element of B and 6 is not an element of A. Either one of those would do the trick. So A is a proper subset of B. Does that make sense?
Yes.
Good. So I recommend that you review the class notes. You can go back and look at the WebAssign, and you can
Okay.
also look at the quiz and the homework problems that were on the special homework. Although those solutions aren't posted, if you want to look at the solutions to one of the special homework problems now, that would be fine. We can
Okay.
certainly do that now. Is there any particular problem that you would like to look at the solutions for?
I think one of them was.
So tell me if you're looking at special homework or quiz, or are you looking at,
I'm looking at the special homeworks right now.
all right, so maybe special homework 2?
Yep, that was the one. Yep.
That was one where we talked about subset stuff. Okay, so
Hmm.
let's take a look. What problem would you like to look at?
It was 6A. I think it was question 6. I didn't get any of those wrong.
Okay. Oh, yeah, that was a kind of fun one because then we practiced about the cross product definition, right? Right? Let's just review cross product. Given sets A and B, and in fact, you can't play this game if A is empty or if B is empty. So we're going to say they're both non-empty. I didn't get into that with you, okay? But
Hmm.
it turns out you can't play the cross product game if either of these is empty. But if they both have elements, we define the cross product, also called the Cartesian product of A and B. And the notation, it's denoted by we just write A cross B as follows. Well, the elements are ordered pairs, all right? A cross B, it's a set of elements that look like this, parentheses, little element, little a, it's going to come from set A, comma, the second coordinate, little element B, coming from set B, and then we close that up. It's an ordered pair. Do you remember that from high school? Maybe from graphing an ordered pair on the XY axis?
Yes.
Okay, so here, the general definition of a cross product, besides just the reals crossed with the reals, which is what the XY plane is, it's, hey, A can be, the first coordinate can be any element of the reals, the second coordinate can be any element of the reals. But in general, we just say, hey, for any two sets, A and B, the set A cross B is the ordered pairs little a, comma, little b, with parentheses, such that the little a is an element of set big A. So the first coordinate, again, comes from the first set. And the second coordinate, little b, comes from the second set. Okay, so they sort of match up. Let's look at an example. If we let A be the set containing, let's call this 1 and 2. And then let's let B be the set containing little a, little b, and little c. Now, well, you might get confused there. Maybe I'll call them something else so that you don't get confused. Maybe I'll call these little x, little y, little w. But the point is, A's got a couple of elements, the numbers 1 and 2. B's got 3 elements, the letters x, y, and w. And then if we want to find each set below, we can play the game. We can say, let's find A cross B. But then we can turn around and we can say, let's find B cross A. And then we can turn around and say, okay, that's fun. Let's find B cross B. So let's practice that first. And then once we understand the cross product, then it makes sense for us to try to work that problem. Okay, you with me?
Yes.
All right, so let's find A cross B. The first thing we want to ask ourselves is, well, how many elements, how many ordered pairs do we expect to find in A cross B? Well, we can count. How many choices do we have for the first coordinate when it comes from this set A?
2.
2, yeah. How many choices do we have for the second coordinate when the second coordinate has to come from the second set B?
3.
So the total number of ordered pairs are 2 choices for the first coordinate times 3 choices for the second coordinate. Grand total of how many elements?
6.
That's right. So here we go. We'll take a first coordinate from A. Let's just grab the 1. All right, that's our first coordinate. We're building our first element. What could we put for the second coordinate as we build this first element?
X.
Yeah. And we just close that up. That's our first coordinate. See how the symbols are different from set brackets? These
Mhm.
are ordered pairs, soft parentheses. You with me? All right. Can we build any other elements using the element 1 as the first coordinate?
We could do 1 comma Y
Yeah, exactly. Keep going.
and 1 comma W.
Perfect. Yep. Now, that exhausts all the different possibilities using the element 1 from A, because we've mixed and matched it with every possibility from B. Do you see that?
Yes.
All right, so now what should we do?
The 2's.
Yeah, the 2's. So you tell me what to write.
2 comma X.
Perfect.
Then 2 comma Y.
Yep.
And then finish it off with 2 comma W.
Does that make sense?
Yes, kind of.
Fantastic. Hey, Kaden. So now we're going to build
Hey,
B.
Professor.
Hey, let's build B cross A. Well, how many elements, and I'm talking about ordered pairs, do we expect to find in B cross A?
Wouldn't it be the same amount?
It's the same
6.
number, but the elements, yeah, we'll have 6. But the number of elements, while the same, doesn't mean the elements have to be the same, does it?
No.
So what would be a good element to throw into B cross A?
Would it be like X1?
Yes, because the first coordinate has to come from set B. So X is one of those first coordinates that are possible, and we can mix and match it with something from A for the second coordinate. X1 is good. What else could we throw in there?
X2?
Yep. Then what?
Y1,
Yep. Keep going.
Y2,
Perfect. Keep going.
W1,
Nice.
and then U2.
Very nice. All right. But these are not the same set at all, are they? Notice how A cross B is not a subset of B cross A because there are elements in A cross B. In fact, just pick any element from A cross B. It's not an element in B cross A. Like 1 comma X is an element of A cross B, but 1 comma X is not an
Is
element
that
in B cross A. So A cross B is not a subset of B cross A. And B cross A is not, oh, I meant to write A cross B. A cross B is not a subset of B cross A. And also B cross A is not a subset of A cross B. Does that make sense?
Yeah.
How many elements would be in B cross B?
9?
Yep, and I'm going to leave that for you to do later, okay?
Okay.
All right, now that we understand the cross product and we understand the empty set, there was one thing you had to look up to work number 6. I always like to give you one thing that you have to look up. And the one thing you had to look up was intersection. All right. So in number 6, you had to look in the book for the meaning of the intersection symbol. It's an operator symbol, like subset. And this is the idea. Here's the definition in case you weren't able to look this up. A intersect B is the set of all elements that are in both A and B. Okay, so here's an example, just a silly little example. If we let A be the set 1, 2, 3, 4, and B be the set containing 3, 4, 5, 6, what is an A intersect B? The elements that are in both the sets. It's like this. If you have a picture of A and a picture of B, the intersection set is the elements they share in common. Okay.
Would it be 3 and would it just be 3 and 4?
Yep. Okay, so that's what you had to look for. But other than that, then you should be able to work number 6 on special homework 2. Let's just see what we were trying to do in number 6 in special homework 2. You were asked to let the universe, and we talked about the universe sort of being the biggest set around, let the universe be this set. I just gave you a set. I don't know how much we talked about it being called the universe, but the point was I gave you a set that had 10 elements in it, right? And you were asked to build 3 subsets of this set U. So we know what a subset is. So we're going to take subsets of this big set, call them A, B, and C. And then this was the game. You got to build your A and your B and your C with 3 properties. The first property is that you wanted to pick an A and a B so that A is a proper subset of B. And we've reviewed proper subset, right? It means A has to be a subset of B, but B should not be a subset of A. In some sense, B has to be strictly bigger. Then if you looked up this symbol here, this just means B and C share no elements. That's what the intersection being empty means. B and C share no elements. They just don't have anything in common. They don't touch each other at all in terms of their elements. And then the last thing was that A cross C needed to have or has exactly 12 elements. Now you understood building the cross product really well. So let me just ask you, just sort of off the cuff, what are some different choices for sizes of set A and set C that would guarantee that A cross C has exactly 12 elements?
3 and 4.
Yeah, A could have 3 elements and C could have 4 elements. So we can start thinking about, okay, when we build A, we can make A has 3 elements and C can have 4 elements, and that means that this particular property will work out. Good. Now, when we pick the A and the B that we're constructing, we want to make sure that everything that's in A is also an element of B, right? Because And we want B to have at least one element that's not in A because we want A to be a proper subset of B, right?
Mhm.
This and so you could say this means right here, this means that the size of A cross C would equal 12. Okay, that was important. Okay. I mean, this is a notation. You don't have to use this, but I'm just teaching it to you. When we put absolute values around the name of a set, we're talking about, the size of the set, how many elements it has. Again, we didn't go over this notation, but I'm just showing it to you now. We could write it with words. All right, so we want to pick an A and a B where A is a proper subset of B and A has three elements. So what do you think you might try for your A and your B?
For A, you could do 1, 2, 3.
That's an obvious and good choice. I like the obvious. Then what about for B?
0, 1, 2, 3,
A,
or
a
1,
zero?
2, 3.
Yeah, you got to keep these as subsets of the universe. Good. Because we were told to explicitly build A, B, and C as subsets of this. Very good. So far, so good. A is a proper subset of B. A is the right size if we plan to build a C that has four elements. Now we've got to build a C so that B and C share no elements. Again, that was the one thing you needed to look up. So what did we make C?
6, 7, 8.
Good. Is that big enough to make A cross C have 12 elements?
um, 9.
Uh-huh.
Yeah, 9. Because it has to be 8 times. I mean,
Yep.
3 times 40.
Yeah, four elements because 3 times 4 will be 12. I think that's going to work out. So let's just verify. A is a subset of B, right?
Mm-hmm.
Because every element in A is in B. All right, so that checked out, right? B and C share no elements, right? So we got the fact that B intersects C is empty worked out, right?
Mm-hmm.
And what was the last thing we had to do?
A times C has exactly 12 elements.
A cross C. Okay, yeah, the elements have commas between them, but when we write the whole set, we don't put a comma between them, we put a cross. But a comma would kind of make sense, wouldn't it? A cross C has 3 times 4 equal 12 elements. That's enough. You don't have to list them all. If you say this, I know you know what you're doing.
Okay.
And that would be the way that you could work that. Does that help you now with the set theory?
Yes, ma'am.
Now, I know that some of those do nows and some of those true false, are sort of tricky, but
Mm-hmm.
those are things you just need to sit with and look at and think about. Go through the class notes. We did some examples in class, and you've got your quiz solution. Uh, okay. Did you
Okay.
did you do okay on number 5
Number 5.
for the special homework?
2. Special homework number 2.
No, I mean problem number 5 on this special homework too, because it was a problem about sets.
Yeah, I believe.
Where
Yeah,
I
I got
gave
that
you
one.
an X, a Y, a V, and a W, and I
Yeah,
asked you true or false. How did you do on that?
I did good on this one.
Okay, now did you do good on that one because you did it yourself or because you used
I used chat to help me study, and it was probably like a similar thing though.
Chat GPT to do it?
To study, yeah. Not to do it though, but to study.
Well, there's really no way to do that problem you can't really study that problem unless you just put it in. But anyway, go back and try to do it now without peeking.
Okay.
All right.
All right.
So review question. See, that's the problem with homework, that you're doing.
Yeah.
Um, if it's a true false, I don't have much way to figure out if you really thought about it on your own carefully or if you just chat GPT'd it. If you chat GPT'd it, you missed an opportunity
Okay.
because you won't be able to use that on the test. But anyhow, Um, I understand the temptation. I really do. All right, Kayan, you've been here this whole time. I'd like to give you an opportunity to ask questions.
Yeah, I wanted to ask about well, when we were in our quiz the other day, we had like truth tables.
Yeah,
I find myself having just like I'm still trying to get that down.
all right. Truth tables can be used uh, for several different things. Let's just talk about the different, do you know the different ways we might use a truth table?
Um, yeah, I mean I have it written down.
Okay, so we can, use a truth table to see if two statement forms are logically equivalent or not, right? If
Yep.
when we compare the columns, you know, if their columns are identical, we can call these forms, let's say we call them curly A and curly B, okay?
Hmm.
If their columns are identical in the truth table, we say curly A is logically equivalent to curly B. But, you know, if their columns disagree in one or more rows, then they are not logically equivalent. And we just put logically equivalent symbol with a slash through it, okay? We can also use a truth table to decide if an argument form is valid or invalid. And I'm not going to write out the four steps, okay, in that process, but
Hmm.
you can find the steps um, on quiz 2, which I emailed to everybody. Did you get the email where I sent you the solutions to quiz 2?
I did see that. Yep.
Or in the good stuff folder, and the subfolder was chapter 2 materials. And then there was a document called 263 algorithm for validity. So the steps appear there and validity and some examples. Uh, are you able, and then sometimes I think on the WebAssign, um, you were asked to check if a statement form is a tautology or a contradiction. Remember that? A
Yep.
tautology is always true. A contradiction is always false. All right. So some of the do laters that we looked at, like on this application to see if two statement forms are logically equivalent or not, let's just look at an example here and let's work through um, that. Or do you need help more with arguments than with validity? I mean, argument validity than with logical equivalence. What do you need help
Um,
with?
I would say the
or just truth tables in general?
I mean, yeah, I could definitely go over both, but I definitely more so
The road.
um yeah, it's the logical equivalence, but also yeah, I would like to go over all if I could.
Oh, okay.
Well, not too, yeah.
Well, listen, let's just say we're asked this.
Yeah.
Are these two statements logically equivalent? P implies Q, not P implies not Q. Okay, so we'll call this one 1 and we'll call this one 2. Okay?
Mhm.
All right, so we're going to build a truth table and we're going to build up to a column for P implies Q, and we're going to build up to a column for not P implies not Q, and we're going to compare their columns. If their columns are exactly the same, then they're logically equivalent.
Cool.
If they differ in even one row, then they are not. You with me?
Yep.
How many rows are we going to need in our truth table?
4.
Well, yeah, because we have P and we have Q and just P's and Q's.
Yep.
So we're going to make a column for P first and a column for Q.
Mhm.
All right, we're going to need 4 rows. What do we put under P? And we put these in alphabetical order.
So true, true could be false, false.
Yes, good. All right, when it's a 4-row situation with the variables in order, you put true, true, false, false under the first variable, and under the second variable, we put true, false, true, false. And that way we are mixing and matching every possible truth value for P and Q, and we don't miss any. You with me?
Yep.
Now we know we're going to need to build up to not P implies not Q, so it's okay. It doesn't really matter what order we build these columns, as long as we wind up with these two, okay?
Yep.
We don't need any extra columns right now to evaluate if P then Q. We've got everything we need for that. So let's go ahead and make the column for if P then Q. All right. Now the rule, do you remember the rule for evaluating if P then Q? Here's
Say okay.
the rule for evaluating if P then Q, or P implies Q. Do you know how this column should look?
Yeah, if P is okay, then Q follows.
Yeah, if P is true, then Q must follow. So let's look in
Okay.
row 1. P is true. So now we check and see if Q followed. P is called the hypothesis. Whatever's on the left of the arrow is the hypothesis. To the right of the arrow is the conclusion, right?
Right.
So in row 1, is if P then Q true?
Yes.
Yes, because P was true. Then we look at Q, and yeah, it followed. It was true the way it's supposed to be. So that's true there. Great. What about in row 2?
Would it be false?
That's exactly when it's false. The hypothesis P is true, but the conclusion, which is Q, did not follow. It's supposed to follow, so this is where it fails. Let's look at row 3. Notice in row 3, the hypothesis P is false. What do we
So
know about the if-then?
would it also be false?
That's what defies intuition. When the hypothesis is false, if P then Q doesn't say anything
It's
about what,
true.
Mm-hmm.
thank
So the answer is true because it's still true even though the hypothesis it's false. Does that explain it?
Okay, I'm going to state the rule. And I'm going to try to explain why it's true. When P is false, this statement, if P then Q, doesn't say anything about what should or should not happen in the instance that P is false. If P then Q only tells us what should happen, in the instance that the hypothesis P is actually true. See what I mean?
Yep.
So in row 3, when the hypothesis of if P then Q, namely P, is false, the if then is true by false hypothesis.
No.
So what do you think the truth value of if P then Q should be in row 4?
It's true by false hypothesis.
Exactly, because again, if P then Q doesn't care about Q unless P was actually true to begin with, and it's not here. Great.
So if the hypothesis isn't, if that isn't true, and then that would make the if then statement true
Yes.
every
Very
time.
good. And and then when we get to this one, this if
Mhm.
not P, then not Q, well, what is the hypothesis of this second statement?
Not P.
So we'll be checking out not P as our hypothesis. It's the same test, but it will now be applied to not P as the hypothesis. Does that make sense?
Yes.
I'm so glad you asked about this. This is really good, and it's often what students have difficulty with. Well, to prepare to build a column for if not P, then not Q, let's go ahead and build our column for not P, shall we? And let's go ahead and build our column for not Q so we can really get a good look-see at those. See what I mean?
Oh.
All right, so let's go ahead and fill in the column for not P. Of course, the not just flips the bit, right? It just flips the column for P to its negation. So here we go. What are we going to put?
False, false, true, true.
Very nice. And folks, if you choose to make F's and T's, make sure I can distinguish them. If you use pen, bring white out or use a pencil. What about for not Q?
It would be false, true, false, true.
Exactly. Great. So now we've got all the bits and pieces, and it makes sense to now go ahead and evaluate if not P, then not Q. You with me?
Yep.
All right, let's do it. In row 1,
If not P, then not Q. Would it be true by
right,
false hypothesis?
perfect. Row 2,
It would also be true.
row 3,
It would be false.
exactly. Row 4,
True.
great. So now we're ready. Let's take a look at our column for if P, then Q. Let's take a look at our column for if not P, then not Q. And what can we conclude about whether or not these two are logically equivalent?
Not
Yes. And why?
their columns don't match.
Yep,
Yeah.
their columns do not match. So they are not logically equivalent. And it's fine with me if you put LE. In fact, this is called the original. Do you remember what this one is called?
Said the original.
All right, this
That's a
one.
That'd be the
negation.
negation. Yeah.
No, this is called the inverse, folks.
Oh.
The bits and pieces are negations, but this is actually the inverse of the original. You need to go back and you need to review. The sisters, the sister conditionals. Okay, so if the original is if P then Q, and so we'll just, call it that. Then we have if Q then P, we have if not Q, then not P, and we have if not P, then not Q. Okay, there are 4 altogether, but these are called the 3 sisters of the original. Anybody remember what this one's called?
You the
It's called the converse.
um,
Yeah, it's kind of,
Lotus Bottom.
pardon? This is, I believe this is section 2.3. It might be 2.2. All right, do you know what this one is called, the third one? If not Q, then not P, relative to the original. This is the one with the longest names.
Inverse error.
Contrapositive. Not if not P, then not Q is the inverse. All right. So listen, we've got 4 argument forms. 2 are valid, 2 are invalid. But those argument forms will make more sense if we understand a couple of things. The original and the contrapositive are actually logically equivalent to one another. The converse and the inverse are actually logically equivalent to each other because they are contrapositions of each other. Look at how we get from the original to the contrapositive. Look at the process. The P and the Q switch places. See that? The P and the Q switch places.
Mm.
Plus, not only do they switch places, they both get negated in the contrapositive. So to get from the original to the contrapositive, we change everything we possibly could change. See what I mean? We switch the position of the P and the Q, and we negate them both. And this is the very longest word of those words. Contrapositive is the most involved word. That's one way to remember that these two are the original and the contrapositive, and they are actually logically equivalent. So I'll ask you to do later. Confirm that P implies Q is logically equivalent to not Q implies not P using a truth table. That'll be really good practice after we're done with office hours tonight, okay?
Yep.
And then we already confirmed that the original is not logically equivalent to the inverse. Hence, Divine, you're right. That's an inverse error situation if we look at argument forms. But the converse and the inverse are logically equivalent. So in fact, this was a do later I asked you to do some point. You can confirm also that Q implies P is logically equivalent to not P implies not Q. And you can also confirm that P implies Q is not logically equivalent to the converse if Q then P. Like you could just make one big truth table and put all of these 4, right? You could do all of it, just like put all 4 and then make their columns. It's great practice for evaluating the if-then, with different hypotheses and conclusions, right? And you
Yep.
can see which all are logically equivalent to the others. And also, if you forget on the test, you can quickly make a little truth table to help you remember. Okay, so in WebAssign, you had many exercises where you were asked, no, you were given a conditional statement in ordinary English, right?
Mm.
Informal, just ordinary English. And you were asked to find the converse, the contrapositive, the inverse, but also the negation. Let's talk about the negation. All right, so let's just recall how to negate if P then Q. To negate if P then Q, we're going to use the rule. The negation of the quantity if P then Q, or the negation of P implies Q. Does anybody remember what it is?
That's P implies not Q.
Almost, almost, so close. But
Wait,
let's just
not P
stop.
and no P and not Q.
Yeah, it's not an if-then statement. The negation of an if-then statement, folks, is not another if-then. Because remember, we learned an if-then is universal. Its negation cannot be an if-then because then it would be universal. And this is the negation of a universal. When we're negating if P then Q, we're negating a universal statement because if P then Q is universal. This is not an if then because it's not a universal. Because when we negate a universal, we don't get another universal. We get an existential. Not a different universal. Not an if then. So that can help you remember that if you do remember, and you should remember that it's called the universal conditional for a reason. Every if-then statement is a universal statement. When we negate a universal, remember we always get the other.
It's an
Yeah,
existential.
we get existential. So there were a lot of WebAssign problems. And I am going to post these notes, okay, tonight after we're done. But let's just go through the famous argument forms, and we can verify one or two of them. The 4 famous argument forms, because we still wanted to look at the algorithm for argument validity, right?
Right.
Well, this will kind of kill 2 birds with 1 stone. But at 8, I am going to take a 5-minute break, and I'll just pause the recording. We can go a little longer than usual tonight, but I'll need a break at 8. Is that okay, gentlemen?
Of course.
Thank you. All right, so remember, we've got P implies Q. It is logically equivalent to not Q implies not P. And we have the converse, Q implies P. It is logically equivalent to the inverse, which is not P implies not Q. But these two are not logically equivalent to the other two, okay? So let's just practice writing the names of these 4 sister forms up here. If we call if P then Q the original, what do we call if not Q then not P?
The contrapositive.
Nicely done. And then what do we call if Q then P?
The inverse.
See
The converse.
Yeah. Like Converse sneakers, you just look at your feet.
Right.
To get from if P then Q, just look at your feet. Flip the head and the toe.
Got you.
I know it's silly, but hey, it works for me.
That kind of stuff helps me like remember. So
All right, just the head and the toe flip. Converse,
cool.
original. And then the inverse and the converse. Because actually the inverse is the contrapositive of the converse. Because look how we get from the converse to the inverse. We flipped everything that we could. We took the P and the Q and they changed places. And they both got negated when they changed places. See what I mean? So
Yep.
that procedure for building that logically equivalent contrapositive holds no matter what you're building the contrapositive of. But this is called the inverse of the original, even though it's the contrapositive of the converse. Anyway, let's look at an example. Since I'm building these notes on the fly, I'm just trying to make sure I put stuff in order. I think it's going to be example 5. Verify that modus tollens is a valid argument form. All right, I'll remind you what modus tollens looks like. They all start, these 4 famous ones look the same. They all start with the very same first premise, if P then Q. The second premise of modus tollens is not Q. Therefore, the conclusion is not P. So here's a premise, here's a premise, here's the conclusion. There might, listen, these 4 famous argument forms only have 2 premises, but you saw on the quiz and homework argument forms that have more than 2 premises. An argument form doesn't have to have 2 premises. It could have 1, it could have 5, okay? But the 4 famous ones all have 2 premises, and the first premise is always the same. If P, then Q, okay? This is a valid argument form, and we're going to use our algorithm. Again, I'm not going to write that algorithm down tonight because you've got it written down in several different places, okay? However, let's go ahead and execute it. First, we make a truth table with a column for each premise and for the conclusion. All right, so let's see. This is a premise. This is a premise. And not P is our conclusion. Do you agree? I'm going to do it efficiently because when you're writing the test, you probably are going to not want to rewrite any columns. All right, so we've got premise 1 here. If P then Q, we've got premise 2, which is not Q, and we've got the conclusion, which is not P. Okay, under P, it's true, true, false, false. Under Q, it's true, false, true, false. All right, I'm going to take a little break, but you gentlemen can keep talking. I'm going to pause the recording, but you can talk to each other and go ahead and fill that in, okay? All right, so let's resume our recording and let's go ahead and work through this. Keeping in mind that in this example, we only happen to have 2 premises, but we could have more. All right, what went under not P?
Said false, false, true, true.
Nice. What went under not Q?
False, true, false, true.
What goes under if P then Q?
I said true, false, true, true.
All right, that's step 1. We have our truth table with a column for each premise, and they are labeled, and a column for the conclusion. And we do want to do that labeling because now in step 2, we identify the rows in which all premises are true. All right, are all the premises true in row 1?
Nope.
How about in row 2?
No.
How about in row 3?
Nope.
How about in row 4?
They are.
Yep, this is a row of interest. It's our only row of interest. Could we have more than one row of interest?
Yes.
Yes, we could have several rows of interest. And now we're going to find the truth value of the conclusion in the rows of interest. So let's look at the conclusion. Isn't it nice that we have our labels column, our columns labeled?
Yep.
So our truth value of our conclusion is true. And so what about the argument form? Valid. The argument form is valid. Because the conclusion is true in every row of interest. Now, we could go to our special homework number 4, or was it number 3, where you had a different argument form. Let's take a look. Let me go and look at special homework number 3. I think that was our little argument one.
So just to clarify,
Yes.
it's valid in every if it's true in every row of interest. So if we had like say we had 2 rows of interest, it was true in one but false in another, that would invalidate the statement.
That's right. Let's take a look at problem 2 from special homework 3. In that particular special homework, the argument form looked like this. If P then R, Q, or if Q then not R, therefore not Q or R. Again, in this case, we have 2 premises, but we could have more. In our quiz, we had 3 premises, right? All right, so here we go. How many rows are we going to need in our truth table? So, yeah. Oh, 4? Look again.
Sorry, 8.
Yeah, if this argument form is valid or invalid. And it is 8 because we have 3 variables, right? We'll put them in alphabetical order. P, Q, R. So under P, we're going to put true, 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 right? 4 truths. I like to settle my eye down. And then false, 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 false. What do we put under Q?
True, false, true, false.
Nope.
No.
True, 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 false, false. So it's true. You split the 4 in half. Half of
Got you.
4 is 2. So it's true, true, false, false, true, true, false, false. All right.
Yep.
Then you split 2 in half, and that's 1. So that's when it alternates.
Yep.
That's real important. All right. We're going to build it. Go ahead.
I'm sorry. And that just so I just want to look at this for a second. So you said split the 8.5. I'm sorry, you split the 4.5, and then you split the 2.5.
Yeah, but we
Does
originally
that
originally did split 8.5. 8 in
okay?
half to get 4 truths and 4 falses, because half of 8 is 4, then half of 4 is 2, and the half of 2 is 1. See?
Got it.
If it was a P, a Q, an R, and an S for our variables, we'd have 16 rows, and we would have 8 truths, followed by 8 falses, then 4, 4, 4, 4, 2, 2, 2, 2, 2, 2, 2, and alternating would be the last. See what I mean?
Got it. Yep.
All right, so we've got everything we need to go ahead and build the column for premise 1. That's P implies R, okay? Doesn't really matter what order we do this, as long as we get a column for each premise and the conclusion. Then to build up to premise 2, I'm going to first build a column for not R, so I don't have to think too hard when we build the column for if Q, then not R. Do you see my reasoning with that? I just don't want to
I'm
think.
sorry. Could you say that again?
All right.
I'm sorry.
We want to make a column for the second premise. It's got a Q. We have the column for Q. It's also got a not R, though. I'm going to build the column for not R first, so that then when I'm evaluating if Q, then not R, I can look directly at the hypothesis Q, the conclusion not R, evaluate the if then using the rule for evaluating a conditional, and it won't make my life so hard. I won't have to think so hard. Does that make sense?
Yep.
So not R will be false, true, false, true, false, true, false, true. You with me?
Yep.
And then we'll be able to build the column for premise 2. Then we're going to want to build a column for this conclusion. Let's look at the bits and pieces. There's a not Q. Do we have a column for not Q yet? Nope. So let's build a column for not Q. Then we'll have the column for not Q. We already have the column for R. We'll be able to OR those together and easily find the truth value of the conclusion, not Q or R. Does that make sense? See, we're just doing a little bit of extra work, but it makes it so that it's pretty clear we're going to get the right column for the conclusion and for the premise too. If we do that little bit extra work, then we'll find the rows of interest because we'll see the two premise columns and we'll be able to check when the premises are both true. And then we'll finally look at the conclusion and see if it's true or false in each row of interest, but we only care about the rows of interest. Because remember, in argument form, this argument really looks like this. It says, if P implies R and Q implies not R. So we and those premises together. If those together imply the conclusion, which is not Q or R, see, we're really evaluating that if then. This is our premise 1 anded with our premise 2. That's why we only check when this hypothesis of the argument is actually true. Because if the hypothesis of the argument is false, then the if-then, the argument is a big if-then, will be true by false hypothesis. So we don't need to do any work. If either premise is false, this and statement, which is the hypothesis, it's all the premises anded together, will be false, and we don't care. The if-then will be true by false hypothesis if either premise is false. Okay, does that make sense?
Yeah.
I know it gets a little deep. Now things get a little deep, right? All right, let's execute the algorithm. Let's go ahead and build our premise 1 column. If P, then R. Okay, so row 1. If P, then R is true. Yeah, because true implies true is true. Row 2.
Be false.
Yeah, because true implies false fails. Row 3.
Be true again.
True implies true is true. You with me, everybody?
Mm.
Row 4.
False.
Because true implies false is false. Row 5.
True.
True.
False hypothesis, right?
Yeah.
In
And
fact,
the
what's
same for the
happening in
rest.
5, 6, 7, and 8?
They're all true.
True.
They're all true. That's nice. Great. Now we're going to evaluate premise 2. If Q, then not R. Okay, so here's our Q column. That's our hypothesis now. Here's our conclusion column. You with me?
Yep.
All right, row 1. If T, then F. What is that?
Q, then not R. That's true. Wait.
True.
If Q, then not R. That'd be false.
Yeah, why?
Because not R was false.
Yeah, we have true hypothesis, Q,
So I was looking at the R.
false conclusion. So if true, T implies false, true implies false is false. Good. Row 2. True, because true implies
Be
true, right? True implies true is true. Row 3.
Be true.
By false hypothesis, because Q is false. Good. Row 4.
True.
Good. Row 5.
Would be false.
Uh-huh. Row 6.
Be true.
True implies true is true. Good. Row 7.
False. No, that'd be true
Why?
because of the false hypothesis.
Perfect.
And the same for the last one.
Row 8. Yeah. Let's say 6, 5, 7, and 8. Okay. All right, great. And then now we're going to build our column for our conclusion, but first we're going to quickly flip the bit and build our not Q column. False, false, true, true, false, false, true, true. You with me?
Yep.
Now we're going to OR Our inclusive OR. We're going to OR together, not Q, ORed with R. So here we're going to try to be careful, right? Here we go. Row 1.
True.
Yeah, because R is true, and that's enough to make this OR operated statement true.
Yep.
Row 2.
Be false.
That's the only place that the OR fails, if both components are false, and they are both false in row 2. Good. Row 3.
True.
Row 4.
True.
Good. Row 5.
True.
Yep, because we have R true. That's enough to make the OR statement true. Row 6.
False.
Good. Everybody with me? Divine, you with us? Row 7.
True.
And
And
row
row 8 is also true.
Okay. So great. Step 1 is done. We have constructed the truth table with a column for each premise and a column for the conclusion. Now we find the rows of interest, the rows in which all the premises are true. We need them all to be true to care, because only if all the premises are true is this conjunction, this and statement, which constitutes the hypothesis of the argument.
I'm sorry, I have a question though.
Please.
So why do we have to do the inclusive or for the P implies R or Q implies not R?
We're not. There is no
Okay.
or operator in P implies R. There is no or operator in Q implies R. This is the implication, the if-then operator, the conditional operator in those two. But there is an or operator in the conclusion, you see. The conclusion can be a compound statement involving any operators at all. Here it involves a not, and it also involves an or. Okay? Every argument form is different. You have to just read what is actually there and evaluate what's actually there. Does that make sense?
Yep.
All right,
Okay.
let's now find the rows of interest. Those are the rows in which all the premises are true. In this case, we only have 2 of them. Okay? Here we go. Row 1. Is it a row of interest? We're looking at the premises.
No.
Yeah, we're not looking at the conclusion. We're only looking at the premises. It's not a row of interest because the second premise failed. See, that means that this premise right here is false. That means the hypothesis of the argument is false, because when you have an and the hypothesis is a big and statement with the premises anded together, if one of the premises fails, then this and operated hypothesis is false. And the argument, which is the if then, will be true by false hypothesis. So row 1, we don't care about. What about row 2?
No.
No.
Yeah, because premise 1 is false. Row 3, do we care?
True.
Yes.
Yes.
Yes, it is a row of interest because both of the premises are true. So we're going to go back later and check that thing out. All right, row 4, row of interest.
No.
No, row 5,
No.
row 6.
Yes.
It's a row of interest. Got all true premises. If we had 3 premises, all 3 would have to be true, folks. Row 7,
Yes.
row of interest. Row 8.
Yes.
Yep.
All right, we have 4 rows of interest. 4 rows in which all the premises turned out to be true. Those are the rows we need to look at now for step 3, right? Step 2 is figure out the rows of interest. Step 3 is check out the conclusion only in the rows of interest. So here we go. Here's our conclusion column. We've labeled it. That way we can see what we're looking at. Is the conclusion true or false in the row of
True.
interest? Here. Yeah. Here the conclusion was true. How about in row 6?
False.
Ooh, false. And of course, in row 7 and row 8, the conclusion happens to be true. We'll just be thorough. But the point is, we have found a row of interest, namely row 6, that has true premises, yet the conclusion failed to follow. So this was true. The hypothesis of the argument was true, but the conclusion failed to follow. And that makes this argument
Invalid.
Yeah. Excuse me just a minute. Thanks.
Yep.
I paused it, right? I didn't stop it, did I?
It stopped that you restarted it.
Oh, you mean I actually didn't just pause it? I actually stopped it?
Yes.
Oh yeah, for a moment.
Oh man, now that means there's going to be 2 recordings. Oh well. I apologize for that. I had to take that call. All right. Well, anyway, let's write it up our step 4. What do we think? Well, the argument is invalid because we have a row of interest, row 6, be specific, in which all premises are true, but, or you could say and, but this is a good place to say but the conclusion is false. All right, so that's an example of an argument form that turns out to be invalid. On the quiz, the argument form turned out to be valid. There were three rows of interest, I think, but the argument form was valid because the conclusion followed in every row of interest. Okay.
Yep.
All right. Divine, did you have a particular question that you needed answered?
Yes. So the ones with the circuit and those circuit questions, those are the ones I still don't understand.
All right, let's look at circuits. I'm going to shoot an email. I am actually going to pause this. I'm going to shoot an email to tell people we are. Okay, so let's talk about circuits. Let's look at an example, shall we? So there are 3 things that happen, right? We have a circuit and we have an associated Boolean expression, and it looks a lot like a statement form, but it's all capital variables, but it looks like a statement form. And then we have what's called an IO table. That looks like a truth table, but it's an input-output table. And the idea to understand is this. The Boolean expression, in fact, this isn't even the example. This is just the thing to understand, is understand this. The Boolean expression describes exactly what produces hot, which we mean true, which we mean 1, output. That's the job of the Boolean expression. So given a circuit, the Boolean expression describes exactly what produces hot output. The IO table does the same. All right, so let's take a look at an example. Let's say that we have a Boolean expression, P and not Q and R, or not P and Q and not R. Let's say we have that Boolean expression. Hey, Sakimi, I'm glad you made it. I sent around that extra note, hoping people would drop in case you couldn't make it at 7, because we're still going here. This is a complete description of all the different things that might be input, all the different input states that would produce a true output or a hot output. Think, juice would be flowing in the output wire. So we can construct the I/O table. And then we might be asked to draw the circuit. Of course, I could give you an I/O table and ask you to draw to write the Boolean expression and draw the circuit. Or I could give you a circuit and ask you to write the Boolean expression and construct the I/O table. It can go any of those ways, and you should check out the class notes, please.
Okay. So for this circuit, is it the one that have like the and in a circle, and then there's a line and like lines connecting them together?
Yeah,
Okay.
so let's do the I/O table first. We have three input variables, a P, a Q, and an R, and they are capitalized. And then we have an output column, okay? But these are the inputs. The P, the Q, and the R are the inputs, all right? And it's going to be 8 rows because we have 3 inputs. And they can be true, 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 or hot, 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 cold, 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 cold under P, hot, hot, cold, cold, hot, hot, cold, cold under Q, or hot, cold, cold, hot, cold under R, okay? Now, we can read off exactly which rows will have hot output because this is a description of the input. It's a complete description of the input state. If this happens, P and not Q and R, if this is what's input to the circuit, then we want hot output. Or if not P and not, if not P and Q and not R is what is input as the input state to the circuit, then in that circumstance, we want a hot output. This is called disjunctive normal form. It's this disjunctive form because the big operator, the last operator that gets executed is this big OR. It's
Okay,
normal.
so we don't pick one out of the operators to use to answer the question, or we use both.
Yeah, both of, see, these two can't both happen as inputs at the same time. Because look at what this first input state says. It says P is hot and not Q is hot. So what does that say about Q? If
Q
not,
is
yeah,
hot.
yeah, Q is cold and
Okay.
R is hot. So in the instance that the input wires have P being true or hot, not Q is true, which means Q is false or cold and R is hot. If that happens, we want the output to be 1 because this expression is actually telling us exactly when we should get hot output or a 1 for an output. This other input state says, hey, if P is cold and Q is hot and R is cold, if that happens, we want hot output. So this Boolean expression is in disjunctive normal form. Inside parentheses is a complete description of the input wires, hot, cold, hot, hot, cold. If either of those happen, because this is the or, if this happens or that happens, then the circuit should output a hot wire or a 1 or true. If anything else happens as input, this expression doesn't involve those circumstances, and the output would be an O. So we can read it right off the table. Look, P is hot, so P is going to be a 1. So it's one of these 4 rows. Q has got to be cold. So now suddenly, okay, P has to be hot, Q has to be cold. It's either this row or this row. R has to be hot. Oh, so you see how it's this row right here? This is P and not Q and R, right? P is hot. Q is cold. R is hot. We want a 1 here. Okay, that's the way the Boolean expression works. It describes the input that would give us a hot output. So this is one of them. All right, so let's see. We want to find the row where P is cold and Q is hot and R is cold. So we go, so P's got to be cold. It's got to be one of these bottom 4, right? Because not P, when we write not P, we're saying not P is what's true or hot, which makes P cold or false. Does that make sense? Then Q is hot, R is cold. So P has to be cold. Q has to be hot. Okay, so now we're here where P is cold and Q is hot. Oh, but R has to be cold. So it has to be this row. This is not P and Q and not R. So we want a 1 there. And that's exactly what this Boolean expression describes. This Boolean expression says, hey, if P is hot and Q is cold and R is hot, we want hot output. If P is cold and Q is hot and R is cold, we want hot output. In every other instance, we want cold output. Are you with me?
Okay. So, I'm sorry. Sorry. So it's like we are looking. So so in my head, how I'm thinking about it is, it's like we have the 3 premises and we are just trying to figure out if the conclusion is true or not.
No, these aren't premises.
No, like I'm using that as an example. That's how I'm trying to. That's how I understand it.
I'm trying
Like
to
if we, sorry.
I'm trying to teach you the proper language to
Okay.
use to describe the objects that we're discussing.
Input state.
This is not an argument. There's not
Okay.
a hypothesis and a conclusion. There are not premises and a conclusion. There are input states. These are statements about whether the input wires have electricity running in them or not. This is a description of one of the ways we could feed 3 wires, a P wire, a Q wire, and an R wire into a circuit. This input state says, hey, if P has a 1 on it, and Q has an O on it, and R has a 1 on it, we want the output S to have a 1 on it. So how do we build the circuit? See what I mean? This is an input state. It's associated with exactly 1 row of the IO table.
Okay.
That's one of the times we want to get a 1 out. The other time we want to get a 1 out is if P is cold, Q is hot, and R is cold. If that's what is on the input wires, like no juice, no electricity on the P wire, yes, Q is carrying electricity. No, R is not carrying electricity. We still want to get a 1 because
Okay.
we write the input situations that we want to use to describe where the output is hot. We don't bother describing what produces cold output because we don't bother writing what's false. We write what's actually true.
Okay.
Does that make sense?
Yeah. So if we have like more than 2 of the input states, so that we just do every single thing for each input state.
Yeah, then we would have more 1s. If we had like another parentheses, like we did in the class notes,
Yes.
then you would have another 1. If you had 4
Okay.
sets of parentheses, you'd have 4 1s over here somewhere.
Okay.
Got it?
Okay.
If we only had 1 set of parentheses and it's disjunctive normal form, see, that's the beauty of disjunctive normal form, is when the expression is in disjunctive normal form, it tells you how many 1s you're going to have in your IO table. If we only had one of these, and that was the expression, we would just have one, and the rest would be O's, and we'd be looking at what's called a recognizer. Because a
Okay.
recognizer is a circuit that only has a single one in its output column, and all the rest are O's. Don't worry about that. Let's see if we can build
Okay.
the circuit. All right, so the deal, see, this is just the beauty of disjunctive normal form. Disjunctive normal form gives us this nice complete description and makes it really, really easy to build the IO table without running all the values through the circuit. All right, so now we're going to build this first input state that's going to yield a hot output. So we need a P. Okay, so P is going to come in. It's hot. And we need a NOT Q. So we pull from the Q wire and we build a NOT gate. All right, so, and we bend it so that it's close up to the P. And now we also need R. So I'm going to pull from R, just bend it. I don't need to solder it to bend it. And so we have P wire, NOT Q wire, R wire. These are going to go into an AND gate. See? Okay, we can call this star. Okay, this is our AND gate for star. Now we're going to build the AND gate for the double star. It needs a NOT P. Okay, well, here's the P wire, but we don't have a NOT P, so let's build a NOT P. Let's pull this down, let's bend it, and let's build a NOT P. We need the Q wire. Okay, so here's the Q wire. We'll bend it down and get it close. There's the Q wire. We need NOT R. All right, well, here's R. Let's just pull it forward a little bit, and let's build a NOT R. So do you agree we have Q, we have NOT P, we have NOT R? We put them through an AND gate because that's what's happening. They're getting ANDed together. All of these are happening at the same time. Q is hot and P is cold, which makes NOT P hot, and R is cold, which makes NOT R hot. So we'll have hot here, hot here, hot here, and then that will turn out to be hot. And then we OR those together. Because if we get a hot output here or a hot output here, we want the output to finally be hot. Let's just run these values through. All right, let's run P is 1, Q is O, R is 1. Let's run these blue values through. Okay, so there's a 1 coming in here. There's an O coming in this NOT gate. So what comes out of the NOT gate?
Cold.
Well, if you run if O is cold, okay? If we run a cold wire into a NOT gate, the job of the NOT gate is to flip the bit. It's going to flip it to a 1. And now this R is hot, hot, hot. So that's hot here. So we have a hot ANDed with a hot, ANDed with a hot, and that is hot output right there. You with me? The job of the NOT gate is to flip the bit. So this O that was cold came into the NOT gate and flipped to a 1. That's what the NOT gate does. It flips O's to 1s and 1s to O's. Are you with me? Right. Now, if we did happen to run this 1 and this
Hey,
O.
hello,
Yeah.
Professor.
Yeah.
Sorry, I'm at work, but I have to call my manager real quick, so I'm gonna leave real quick.
Bye.
Okay.
Thanks for telling me. Appreciate that. Okay, let's just to notice this AND gate spit out a hot, but this AND gate won't for the blue out input because 1 is going to come down here and get flipped to an O when it comes out of this NOT gate. This O is going to be an O, and this 1 is going to be an O. It just happens that they're all O's because of the way that I constructed it. And this is an O. But we still get a hot output here because it's an OR at the end of the day. If this happens, or that, and in this blue case, I say this happened, P and not Q and R yielded a 1, that makes a hot output. So now if we run the red values through, okay, so we have an O here, but this 1, when it runs through this NOT gate, it becomes an O. This O, which is R, is an O. O and O and O is O. So that's not going to help. But when we run this O down here through this NOT gate, it becomes a 1. When we run the Q, which is 1, up here into this AND gate, it's a 1 running in there. And this O for R goes to this NOT gate, it becomes a 1. Now we're ANDing together a 1 and a 1 and a 1, and that's a 1. And we get a hot output 1, and that's the circuit. That makes sense, Divine?
Yes, thank you so much. Will the recording be posted because I need to log off because the doctor is right here.
Yep, I'm going to log off now. I mean, I'm going to record it. I'm going to pause and see if Sakimi comes back. I'm going to do that. I'll post it now,
Okay, thank you so
or
much.
as soon as it processes. It's going to take it about an hour to process.
Okay,
All
thank you.
right, bye.